We're going to introduce Newton's third law. And before I do that, I want to quickly review his second law. And we remember that Newton's second law states that the sum of the forces on an object is equal to the mass times acceleration. We're going to be using this here in just a moment. Now, the formal definition of the third law, it states that the interaction between two objects can be represented as two forces having equal magnitudes and opposite directions. So we need two objects. In this case, here we have a person, which can be object 1, and we have a box, which can be object 2. So, okay, we've got the two objects, and it states again that any interaction is represented by two forces having equal magnitudes and opposite directions. So if this person starts pushing on this object and they push to the right, so there's going to be some rightward force due to them pushing on the object. Well, then, according to Newton's third law, there has to be another force. If this is force 1 pushing to the right, then there has to be another equal and opposite force pointing to the left. So again, Newton's third law, it states that an interaction involves two equal and opposite forces. And that's pretty much it. That's everything that we need to know. So if there's a force acting on any one body, then there must be an equal and opposite force that's acting on something else. And what would that look like for something that's not touching? We know that they're still interacting. They have to be because there's a force. So if you're skydiving and you're falling towards Earth, we know that there's some acceleration that's due to gravity. And if there's an acceleration, then there must be a force because we have an acceleration. It's called g. It's pointing downwards. We have a mass. Obviously, the person has mass. Well, then there must be a force. So if there's a force pulling you towards the Earth, then you must be pulling the Earth towards you. And that's very strange, but it is absolutely true. You are being pulled by the Earth, and you are pulling on the Earth due to the force of gravity between these two objects. It's the same as if you're interacting with some push or pull where there's actual contact, where you're pushing on the box and therefore the box is pushing on you. Or you're pushing downwards on your chair and your chair is pushing upwards on you, preventing you from falling into the earth. So whenever you have a force, there has to be some equal and opposite force pair because forces happen due to interactions between objects. Okay, so if that's true, well then, what about some kind of extreme case where there's a truck that's going down the interstate and it hits a mosquito, and the mosquito is flying towards the truck, and the truck is moving towards the mosquito. So, what happens then? Well, according to Newton's third law, when the truck hits the mosquito, when the mosquito hits the truck's windshield, there's some force on the mosquito, and there's some force from the mosquito on the truck. And they're equal. Well, how can that be? I mean, the force should, maybe we think, be greater from the truck acting on the mosquito because the truck's so huge. How does the mosquito cause any sort of force to occur on the truck? Well, if we look at Newton's second law, and this is where we have to take this into account when we're thinking about forces. So a force is equal to the mass times acceleration. So one of the forces we can call it the force of the mosquito on the truck. So let's write that down. Let's say the force of the mosquito on truck. is equal to MA. And then we have the force of the truck on the mosquito is some other MA. So if these two are equal, if the force of the mosquito on the truck is equal to the force of the truck on the mosquito, so this is the mass of the truck. So we know that the truck's mass is very large. And we know that the mosquito's mass is very small. So I'm just pointing a downward arrow, meaning little, an upward arrow pointing upwards, meaning large mass. So this is a small mass, the mass of the mosquito. This is a bigger mass, the mass of the truck. Well, if these two are equal, then this right-hand side has to also be equal. But we said that the mass of the truck is very big, and the mass of the mosquito is very small. So for these two sides of these equations to remain the same because these two are equal, well, then the acceleration has to change accordingly. If we raise the mass, then we have to lower the acceleration. If we lower the mass, we have to raise the acceleration. Now let's see if this makes sense to us, because we know that the forces have to stay the same. That might sound a little weird, but if we think about this for a second, so the force of the mosquito on the truck. Well, the mosquito has very small mass and the truck, M sub t, is very large. So the acceleration on the truck is going to be very, 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 very small. The mosquito is not going to cause the truck to accelerate very much. But if we look at the other situation here where we have the force of the truck on the mosquito, well, the mass of the mosquito is very small. Therefore, the acceleration of the mosquito caused by the truck is going to be very large. This is why when you see an accident that might happen on the interstate between a truck and a car, well, the car is usually in very, very bad shape because the mass is so small compared to the truck. Even though they'll have equal forces in some sort of collision. So even if you have a truck going one direction and the car going the other direction, and the forces of the collision are the same, because the car has such tiny mass compared to the big mass of the truck, well then the car is going to accelerate so much more than the truck. The truck will barely feel it. It'll barely accelerate at all compared to the car. So when we talk about these Newton third law interactions, we call them force pairs. Notice here, everything happens in a pair. Whether you're falling towards the earth and the earth's pulling on you, well then you're pulling on the earth. If you're pushing a box, well then the box is pushing on you. If the truck presses on the mosquito, well then the mosquito presses on the truck. So these interactions happen in force pairs, and we'll typically use, if we have an object 1 and an object 2, well then we'll say the force of 1 on 2, and we'll say the force of 2 on 1 to try to keep track of the objects that are involved in the interaction. And just remember, if these two press on each other, then F1 on 2 has to equal F2 on 1. These are the magnitudes, so the magnitudes have to be equal. Well, what's going to change? The directions. They have to be equal but opposite. So because the magnitudes are the same, that means this quantity, m2a2, the mass of 2 and the acceleration of 2, has to equal the mass of 1 and the acceleration of 1. The only thing that's going to change is the directions that these forces are occurring in. So for example, the mosquito's force is going to point towards the left in this scenario, and the truck is going to point towards the right. So again, remember that the acceleration and the masses are going to vary inversely. In other words, one might increase, one might decrease to keep these two forces balanced, because the forces themselves have to be equal.